In this video, we're going to start our discussion of stacks. So stacks are a pretty important data structure. And as such, we're going to talk about it in 3 different videos. So in this first video, we're going to talk about what a stack is in general. And then we're going to develop this idea of an abstract data type. Okay. And it's because we're going to talk about implementing our stack in 2 different ways. So the ADT is going to give us what our stack behavior is. We'll do this with some pure virtual functions. Okay, and then we're going to implement stacks using either an array, which will be the second video, or as a linked list, which will be the 3rd video in this series. Okay. So the first question to ask here, of course, is what is a stack? Okay, so in this case, a stack is going to be a data structure, I guess the formal definition. Okay, so it's a data structure that is a first in, last out. Okay, so the very first data structure that you add to your stack will be the last one to come back out. Okay, so we think about this. Hope that's a little bit clear. When we think about this, some analogies here is if you have a stack of books. Okay, so if you have whatever books that you have, so you got a math book, so you've got an English book, and you've got a history book. Okay, and here's your table. The first book that you would have added to the stack would have been math. Okay, and then English, then history. Okay, if you can only get one book out at a time, the last one in, history, would be the first one out. Okay, and the last one out would be math. Okay, the other way we look at this is if you have a stack, if you're in the cafeteria and they have a stack of plates. Okay, so there are a bunch of plates there. Okay, I like this because it's important when we're thinking about stacks. All that we can see from a program point of view is just that top. So over here, all we can see is this top. Okay, this data structure has that restriction to enforce certain behavior. Okay, so I can only see what we're going to call the top of the stack. Okay, if I were to remove this one, okay, everything would then move up. Okay, and this one becomes the new top of the stack. At any point, the top of the stack is all that I'm going to be able to see. Okay, so again, we start with an empty stack, and the operations we tend to define are push, where we're going to add to the stack. Okay, we have a top function where we're going to return value at top of stack. And then we have a pop to delete the top of stack. What's it to? Add to stack. Okay, it will add to the top. Okay, delete top of stack. Okay, so let's this is our empty stack here. Okay, so we have a stack, call it S, whatever. Okay, if I were to do an S dot push, let's say A, whatever A is, A would appear on the stack. Okay, the top of the stack would point to A. Okay, if I were then to see out, if I can write it, S dot top, it would give me that A. Okay. If I would do an S dot push B, there's now a B here on the stack, and the top now points to there. Okay. So if I were to do this top again, it would now give me a B again if it were below there. Okay. An S dot push C, we put C there. And again, the top now points there. Okay. So at this point, I don't know how many other items there are. Okay. Again, if I were to do a C out, S dot top, it would give me the C. Okay. And now if I would do an S dot pop, which is a void function, and then do the same thing, the S dot top would refer to the B. And at that point, the stack would look like that. Okay. So that's the basic idea. At any point, you can only see the top of the stack. Okay. That's all we've got. Okay. So let's now look at the code. Oh, sorry, one more thing. One more thing I want to talk about. This idea of an abstract data type. Okay. So again, I mentioned a little bit at the beginning, but the idea here is that I'm going to create this stack adt.h, okay, where I'm going to list all of the pure virtual functions that I need. So when I go to inherit these and implement them either as an array or as a linked list, I can guarantee that each of these will have all of those functions. Okay, that's the whole point of doing an abstract data type. Okay, so I think that will make more sense if we actually do that. So let's go ahead and go over to the code window and take a look. Okay, rather than type it all, I'm just going to go ahead and show you what I've got here. Okay, so again, make sure I'm sharing the file. If not, I'll do the video over again and no one will be happy. There we go. I think I'm for sure now. Okay, so we now have our stack adt.h header file specifying the behavior for a stack. This class that we're developing here has pure virtual functions, so it can't be directly used or directly instantiated. You can't make an object of type stack adt. Okay, they're an abstract class, not concrete. Okay, so any class that inherits from this, that's what it inherits from, anyway, has to implement all of the pure virtual functions we're defining here. So again, the reason we do this so that if we write programs that use the array implementation of a stack, because we have all these functions that are the same, as long as we use those same functions and only those functions, we could substitute the linked list version of the stack into programs and it would not change how the program operates. Okay, again, if you stick to these functions. Okay, so this is something we haven't done in the other examples, but it's always a good idea, and that's to template these classes, which means basically we don't have to create separate versions for different data types. On the linked list version that we did it with integers. We would have to create, we'd have to copy our code, make all those changes, all those find and replaces to have it work for doubles or strings or whatever. So in this case, we're going to take the variable type, call it type with a capital T, that then becomes a class variable that will tell us what we're storing, whether it's a stack of integers or a stack of booleans. Okay, so here's our class stack adt. There are no private functions here, no private data. Okay, we're not storing anything. Okay, we don't know anything. Everything that we need to know would relate to the implementation. Either we need to know where we are in the array, or we need to know the root of the linked list. Okay, we don't have any of that in this super class that's derived to give structure to the subclasses. Okay, so all we have are public functions. Again, these are pure virtual functions. They're virtual functions because of the keyword virtual. They're pure virtual functions because of the equals 0. Okay, and this means basically that anything that inherits this has an obligation, or you get a compile error, to have a function called initialize stack, for example, that is a void that takes no parameters. Okay. So here are the only functions we're going to care about here. So the first one is, again, I just said it, the initialize stack takes no parameters, and it's a void function, and the post condition. So when we have run this function, we have reduced our stack to nothing. Okay. Again, we have to worry later if we're on a linked list. We have to make sure that we're properly deleting things from memory and not creating a memory leak. Okay. Our next function is an isEmpty stack. Okay. That's a constant function. It shouldn't change your stack at all. And of course, the first one will change your stack, so there's no constant there. The isEmpty stack just asks the question. It's a Boolean. Is the stack empty? It returns true if the stack is empty. It returns false if the stack is not empty. Okay. Is full stack, same deal. Okay. And it's a constant function also. It doesn't change the stack. So we're going to answer the question, is there still room left in the stack? Okay. If so, if there's room left, it's not full, we return a false. But if it's true that there's no more room, then it's going to return true that it's full. Okay. Now note that the isEmpty stack and the isFull stack really only have meaning for the array-based version, because when we get to the linked list, as long as we have system memory, which we typically will, there's no maximum size. Okay, but we'll put that in there for the array part. Okay, and then there are the functions we talked about before that are really the essence of the stack. Okay, there's the push. Okay, it's again a pure virtual function with a virtual keyword that equals 0 at the end, and it's going to take a constant reference. So the ampersand means it's the reference to some new item of type. Okay, integer if it's for integers, float if it floats. Okay, and it's constant because that new item shouldn't change. We're just going to, so again, we have preconditions. The precondition here, the stack has to exist, so it's going to give an error. Okay, and the stack can't be full. You can't add anything to a full stack. Okay, but if those preconditions are met, the postconditions are that whatever the new item is, it will be at the top of the stack. Okay, so the constant here, again, just so we're clear, this constant in the parentheses refers to the new item, which will not change. There's no constant over here because you're adding something to the stack will change. Okay, so the next one here is the top function. It takes no parameters and it returns type of type. If it's a stack of floats, it's going to return a float. Okay, this time the constant is over here. Okay, because we're not changing the stack at all. What we're doing is returning that top value. Okay, so nothing changes. So the precondition here, the stack must exist and it can't be empty. If there's if it's empty, there's no top. Okay, the postcondition is the top element of the stack is returned as long as the stack's not empty. If it's empty, it won't return anything. It'll just let you know that it's empty. Okay. Our final function here, which is not constant in any way, is again a pure virtual function called pop. Takes no parameters, so it equals 0, so it's pure. The precondition here, the stack has to exist, can't be empty. And the postcondition is that it will remove the top element from the stack. So whatever's on the stack, it's going to delete whatever at the top of the stack, it's going to delete that. The analogy here is if you're in the dining room and there are plates of all different colors, if there's a red plate on top of the stack, that red plate has now been picked up by somebody, and whatever was under it comes to the top. Okay. So that's it. That's all we have to worry about when it comes to a stack. Okay. So I wanted to go ahead. I was afraid if I did all three parts as one video, it would be gigantically long. Okay. So I didn't want to do that. So I wanted to go ahead and break it up. So keep this in mind when we get to the array implementation. It will be assumed that you understand this part. Okay.